Okay. Hello, good morning. I'd like to welcome all here. Thank you for joining the workshop of our project regarding the increasing the efficiency and reliability of the electricity network. Today we're gonna start with a little bit of an introduction of our project, what have we achieved, and then we will proceed a little bit more with some technical advancements and solutions we have and also achieved within the time frame. And then we will delve deep in one of our pilots regarding, as I said before, to increase the efficiency and reliability of the electricity network. This workshop aims to showcase our solutions, our outcomes, our results, both on technical and research level. So we can start right away. Just a second to share my screen. Presentation mode. Can you see the screen in presentation mode? Is it correct? Can someone confirm? I cannot hear you.
We can see the presentation, but it is not in presentation mode yet, I think.
Now?
Now it is.
Okay, great. All right, I can hear you. Okay. Welcome again. I'm Nikos Dimitropoulos from National Technical University of Athens, and I'll do a little bit of introduction and presentation of our project, BD4NET, which aims to tackle big data challenges on the energy sector. Today, I'm going to tell you a little bit about our vision, our overall solution, and finally, our piloted applications before we proceed more in detail in one of our pilots and their solutions. So, BD4NET is a research project, a European funded research project. It started almost 3 years ago. We're heading towards its end. We already achieved all of our outcomes. So the idea for us, our vision when we started this project was to have many aspects. Most of them you can see them here. The vision was to deliver an innovative energy-specific open analytics modular framework. This means that we apply analytics solution to several energy-related and big data problems. To enable and start an incremental decentralized energy data-driven ecosystem. We have a lot of application all throughout Europe, so that means we need to apply solution in a decentralized manner. As a research project, we needed and we have integrated state-of-the-art technological advancements for this data-driven ecosystem. You'll see more of it later. Of course, to unlock and exploit the economic potential of big data in the energy sector, that means that all of our solutions have also accompanied business outcomes, business models. Will not be more in detail on that today. We focus on the technical and the research solutions. And finally, to enable AI-based cross-sector analytics for smart energy grid management. In general, we use technology, we deploy technology, we implement technology and analytics based on artificial intelligence for several state-of-the-art, very recent, very current energy problems. All of this, you can see it here in a more detailed schema. This is more or less our solution, how we used the data, the big data that the energy sector is dealing with more and more as we advance. You can see here that we have our technological solution have 3 layers, let's say, the BD4NET governance, the BD4NET processing, and the BD4NET analytics. All of these are technological solutions. We have identified 3 pillars. We have proposed 3 pillars, BD4NET, BD4DER, BD4NF. This is where our pilot comes from. Today, we're going to focus on the BD4NET pilots and one of them specifically. All of these come together in a BD4NET marketplace in which our developed solutions, we can offer them through a marketplace for reusability. That might be either data, either complete application, either AI models. All of these are integrated in our solutions. Here is a little more in detail. In general, we have in our project several, we're very happy, very diverse set of stakeholders of the energy sector, DSOs, TSOs, market operators, non-grid assets owners, weather services, of course, residential data, all of the residents, all of these provide data, we call them data hubs, their infrastructure as components to work on the solution. These feed to our stack, let's say, for data integration and homogenization, multi-party data sharing, and off-chain data sharing. This all apply to the governance layer. BD4NET is a governance layer, how we get the data in order to use them in some ways. These ways are the BD4NET processing towards the pilot application, smart data management to make it easy for the stakeholders to understand the data, to share the data, for the data to be interoperable, and create solution on the vertical aspect there. You can see BD4NET analytics. We created analytic services based on AI for our pilot application. This analytics can be and have been deployed as prescriptive analytics, visual analytics, descriptive analytics, and predictive analytics based on our use cases. And all of them come together in our toolbox, which can be used by the stakeholders, researchers, and then fed into the marketplace in which these data or models or complete services can be sold or used. So our pilot application, as I said earlier, we have 3 pillars: BD4NET, BD4DER, BD4NF, 12 pilot overall, too many use cases, too many challenges, but we are optimistic based on our results that we tackle them all. BD4NET this is workshop is for, is regarding predictive analytics to forecast and increase the efficiency and reliability of the electricity network. BD4DER is to optimize the management of assets of distributed energy resources connected to the grid, and BD4NF is to increase the efficiency and comfort of building, and mostly to de-risk investments in energy efficiency. Today, we focus, as I said, plenty of times to BD4NET. You can see here our pilots, our stakeholders, our partners, and their use cases, what they are trying and applied, manage to tackle. We have DSOs, TSOs, local TSOs, local smart grids. Today, we will focus on LSP1 because integrated off-grid data with condition-based monitoring for enhanced predictive asset maintenance. This is the main problem. You'll hear about all of it later. But let's go a little bit more, just the summary, just a brief for all of our 12 pilots. On BD4NET, we also have a cross-functional integration off-grid operation with predictive asset management, the use case we have. Another one is cross-domain functional integration of predictive asset management and grid operation, while coordinating EV smart charging. And another one on BD4NET to cross-functional predict asset management for medium voltage grid planning. This fall over this category of BD4NET. Furthermore, for the other 2 pillars, just a brief again, 5 pilots in BD4DER. One is to use cross-stakeholder transfer learning for flexibility asset forecasting. Another one is to coordinate grid-owned and behind-the-meter asset management prediction to improve grid operation. We also use predictive analytics forecasting of storage in order to improve market reserve participation. Another use case is to predict demand and generation in a small island for optimized local community energy management. And another one, pilot application challenge use cases to predict demand and generation forecasting for optimized local energy community management. Finally, the last pillar, BD4NF for energy efficiency and risk investments, has 3 pilots. And we use predictive and prescriptive analytics to improve energy performance certificates reliability, to use weather enhanced prediction for building thermal comfort, and to use predictive analytics for energy efficiency investment de-risking. All of this is a very, very short summary of our solution, our pilots. Today, I'd like to welcome Apostolos Kapetanios, that will present the technical solution and advancements of our project, and of course, Parida and Nicolo, that will show you a little bit more in detail the BD4NET pilots, and in detail the first pilot, what have we done, what have we achieved, what are the analytics, what are the impacts, and in general, the results and outcomes of this pilot. Further information you may find on our website to go in detail for other pilots, our events, our news, our outcomes, of course, social media channels. We cannot tackle the full project in 10 minutes. Someone came, sorry, it's my name day today, so a lot of people come to say happy name day. So you can see that. So yeah, no further ado. Apostolos, you can take the floor here. Thank you all. Thank you for joining.
Excellent, Nikos. Thank you very much for the introduction. Let me proceed with sharing my screen so that at least we can see the next presentation. So, do you see my screen with the presentation?
Yes, but not in
We see the full
presentation mode.
screen. Oh,
Now,
great.
yes.
Excellent. So, thank you very much, Nikos, for the introduction. Indeed, hello all. And I would like to welcome our participants. My name is Apostolos Kapetanios. I'm a senior R&D architect in European Dynamics. For the next 10 minutes, we can delve in a little bit more detail in the technical layers of BD4Energy after Nikos' explanation. And let's continue by seeing a little bit the BD4Energy technical framework. We can see the main aspects of it from the assets, basically the data sources, and the responsible actors, which feed the data governance layer responsible for interoperability, which is leveraged by the analytics machine learning component layer. It is obviously data management go to analytics, and all this in combination with the services that have been created in BD4Energy, exploited by the marketplace. It's a simple framework, but at the same time, it's holistic, and it represents, gives a very good concept about the whole BD4Energy project. Now, let's continue. We have basically three layers, and the first one, as mentioned before, is the data governance layer. Let's discuss a little bit about the objectives of it. Main objective, it is to implement the BD4Energy data governance according to big data management and modeling best practices, for example, BDVA, etc. To enable the exchange of information between assets, systems, data hubs, and actors in a common interoperable manner. To define a data access policy layer according to cybersecurity, legal, ethical framework and guidelines that we have put down, and they're a very integral part of the implementation process. Data access policy layers, it is very important. We are talking about specific access rights to data sets or services depending user, organization, etc. Even usage control, let's say, functionality. Another objective, very important one, is to develop and configure the modules that will assure the quality of the retrieved datasets. There are specific data quality scripts that are running during the pipeline process. Another objective is the development of a peer-to-peer digital ledger blockchain environment in which we have specific smart contract applications that can be leveraged by the whole project, for example, in notarization process. Another objective is to develop the edge IoT big data management enablers, which can include the elastic streaming data capturing management, a very integral part in the ingestion process. And all of this constitute the interoperability and homogenization layer. Let's not forget that one of the main purpose of the governance layer is also semantic interoperability. Now, if we are to visually represent this process, we can see it in the slide, meaning that for the large-scale pilot datasets, going through the transformation layer and quality checks, we have the data integration needed in order to have the operational data support and land to the analytics and decision support services that we have built in BD4NET. Continuing, in this schema, we can see the data governance architecture. We can see the data process flow through the pipeline management that we have created. And when we are talking about the data flow, we are talking about the data chain from the data providers to data consumers, meaning how from the data sources we arrive to the landing zone of raw data. We continue, as I said before, creating the golden data sources by specific quality, interoperability, and homogenization functions, where we ingest the data either by stream ingest or batch ingest, and we have the data ready to be used by the specific machine learning functions through specific integrity checks and syntactic translation engines, where we leverage the data access policies that we have mentioned before in order to come up to the upper layer of the data governance architecture, where we have specific query engines in order to query the data sets. All this gives us the capability to being able to have a functionality for the data consumers to consume the data sets, the data that they require. So the data governance architecture, as we can see here, also gives us how the data sharing process, how we can share data in the context of BD4NET between data providers and specific data consumers. All of this through specific data governance metadata tags, and all of it built in the infrastructure that we are using in the BD4NET. The second layer, the second technical layer, already mentioned by Nikos, is the analytic toolbox layer. The objectives of the analytic toolbox is to develop the specific data analytic services in order for us to be able to do what? To analyze data in a holistic manner across multiple data sources and different languages. We saw that in the governance architecture, so that we have a very important part of the entire data life cycle from creation to data consumers. Another objective is to handle deliver the libraries and algorithms. This is the important part of the analytics toolbox, so that we can have what? Data knowledge extraction, BI, business intelligence, and specific energy domain analytics. Thus, the layer BD4NET analytics. What we can do, basically, and what we have created, we were able to deliver the tools, methods, and frameworks for processing, visualization, exploration, and querying data in datasets. To deliver the libraries and algorithms for knowledge extraction, we mentioned before knowledge extraction, business intelligence, and analytics. Obviously, to integrate all the different modules of the platform with specific clear interfaces and low level of independence. This is very important. To create a modular framework so that we are able to continuously integrate additional functionality to each module, starting from core set of features and gradually reaching to the desired outcome. This is also our methodological implementation process, always in the context of the pilot case requirements identified in Work Package 2 and Work Package 6. And last but not least, to consolidate and fine-tune the different modules forming the integrated BD4NET platform. What was the result from the implementation taking into consideration these objectives? The data analytic toolbox and the BD4NET integrated web-based platform. Continuing for the analytics toolbox, let's categorize the implementation. We have incremental, distributed, and self-learning analytics. cross-stakeholder transfer learning, declarative, predictive, and prescriptive real-time data analytics, and we can categorize them also, the implementation to visual analytics, dashboard, and report libraries specially focused to the energy domain. And let's continue by seeing some specific examples in this. Our data analytics services. Let's discuss about certain examples. NWP-based midterm photovoltaic production forecasting, large-scale load forecasting at an island level, water pumping systems load shifting, de-risking investments in the energy efficiency actions in buildings, thermal comfort analytics for buildings, IPMVP-based energy efficiency renovation assessment, PV and CPV production, NWP independent short-term forecasting. Another one is the power scheduling optimization between EV charging stations, storage system, and PV panels. Cross-stakeholder transfer learning, we mentioned before knowledge transfer. Predictive assessment and power transformer aging, very important, very helpful for predictive analytics and preventive maintenance. And visual analytics, dashboard, and report libraries for the energy domain. We mentioned that also before. Third layer of the technical implementation, which also we saw it in the framework, the basic schema that we showed before, is the marketplace. So, a main objective of the marketplace in the context of realizing EU-level energy data economy is to boost the wider use of the project results. How? We have new business opportunities. And thus, we magnify the market share of the European data companies by expanding the scope of the BD4NET ecosystem. So by having a marketplace, we are able to expand the scope of the project, but also exploit the project results through a marketplace. BD4NET marketplace integrates and coordinates different services to provide the required functionality. We have in the BD4NET marketplace loosely capped collaborating services. So we have unique services, but also services that we collaborate with each other. And all the functionality is being exposed through a specific REST API. In the schema, we can see a visual representation, a high-level architectural concept of the marketplace. We can see the graphical user interface, the services module and the catalog, services catalog module, and how these modules, these basic modules of the marketplace backend, exploit specific layers as a result of the two previous technical layers. For example, we have the blockchain-based asset management layer that feeds the tokenization access layer of the marketplace. Accordingly, the governance layer that we discussed before and how this constitutes the governance access layer of the marketplace, etc., etc., etc. So that we have machine learning as a service in the marketplace, the implementation integration of third-party services, a simulation as a service, etc. All of this wrapped in a catalog module where we have the data catalog, exploiting the query engine of the governance layer, the computing resource catalog, the machine learning and analytics catalog, basic specific catalogs for all the assets that are present through the REST API and the graphical user interface in the users of the marketplace. So that's all as a description of the technical layers of the BD4NET project. Again, I am Kostolos Kapetanios, Senior Research Architect for European Dynamics. Thank you very much for your patience. I believe at this time I can stop sharing the presentation. And I think that we can move on with our session. And we can move on to Pareto Styrio.
Yes.
Talk to us about the BD4NET pillar, large-scale pilot, and especially it will talk to us about how can increase the efficiency and reliability of the electricity network in the context of this specific pillar of Thermos in BD4 Energy.
Yes, thank you very much, Apostolos. So I will share my screen. Oops. I don't, so just a second. Okay, yeah. You should be able to hopefully see my presentation. No,
Yes, yes, we can see it.
it's why it was working before. Sorry. It's not this one.
You can go to impostazioni di visualizzazione on the top.
Not up.
You see that the second impostazione di visualizzazione. Click and then you can switch, I believe. Inverti.
Oh, okay, okay. Yes. Thank you very much, Nicola.
No problem.
Okay, so good morning to everyone. My name is Pari De Rostilio from ASM Terni, which is the company responsible for the UP7 pillar, the BD4NET large-scale pilots. Just to give you a quick introduction about the company, ASM Terni is a multi-utility operating based in the city of Terni in central Italy, and operating on the municipality territory and the surrounding territory. It provides the local end user with power, as well as drinking water, natural gas, and environmental services. It participates to the project mainly in the role of electric DSO. Indeed, we provide every year with more than 400 gigawatt hour of energy to the 65,000 end users in the municipality of Terni, which counts approximately 110,000 inhabitants. We do so by managing a network which comprise 3 primary substations, 700 secondary substations, and more than 600 kilometers of medium voltage line and 700 kilometers of low voltage lines. As I say, we are responsible for the BD4NET pillar, which is the work package in which 4 of the large-scale pilots, which all are related to the managing of electric networks, see the real-life testing of the BD4 energy solutions. In particular, 2 of these pilots are in the context of the transmission system operators, so basically the management of high voltage grids, and 2 of them are in the domain of distribution system operators. And we will see that one of them focus mainly on the medium voltage grid and the other focus mainly on the low voltage grid. Among the main activities of the work package, we have the integration and cleansing of the datasets from different sources for each of the pilots, of course, using the semantic tools and methods of BD4 Energy, and then the application of the big data analysis using machine learning tools eventually on these integrated datasets. And finally, the report of the real-life process in the 4 different pilots in order to assess the effectiveness of these tools. Of the 4 pilots, LSP1, that will be shown in greater detail in a few minutes, takes place in Portugal on the national transmission grid of the country. LSP2 takes place in Slovenia. The responsible partner is ELES, the national TSO, aided by the University of Ljubljana, in particular the Electrical Engineering Faculty, and Consensus, a company which advanced expertise in the context of remote monitoring and control, especially in the energy sector. LSP3, for which ASM is responsible, takes place in Italy, in the city of Terni, indeed. And ASM is aided in the pilot by Emotion, which is a company which provides electric mobility services as well as engineering for the technical part, since the background of engineering is indeed informational engineering. And finally, the LSP4 takes place in Eastern Turkey, and the main responsible is OEDAS, which is a local DSO. So since LSP1 will be explained with greater detail, I will just give you an overview of the remaining pilots, starting from LSP2, the cross-functional integration of grid operation with predictive asset management. As already mentioned, this takes place on the national transmission grid of Slovenia, and ILES, the TSO, seeks to modernize, automate, and digitalize the planning, the scheduling of the maintenance outages on several on the assets at different voltage levels, at 400, 220, and 100 kilowatt. It does so by leveraging on the wide and diverse existing datasets on which the big data analysis has been applied. And the project delivered a tool, a maintenance scheduling tool for them, that will have a twofold output. On one hand, a yearly general outages scheduling, on which the secondary output will be a bi-weekly update, which will allow them to take in consideration like short-term notice events, like for example, weather forecast or unplanned occurrences, as well as coordination of different operation from the crews from different regions. The success of this maintenance scheduling tool can be seen in the graph on the bottom left corner of the slide, in which, in particular, considering the gray color column, we have the total outages time during the years 2018, 19, 20, and 22, which is significantly higher if compared to the total outage time that will be achieved using the MST, as you can see. So this tool proved successful and will help LS to shift from a maintenance, which is time-based, so with maintenance and therefore outages planned periodically, to a more condition-based one, in which the maintenance is performed only when it's deemed necessary. Moving to the LSP3, for which ASM is the main responsible, we have that this pilot is divided into different use cases. The first one, efficient management of flexibility resources for supporting grid operation, see the local DSO, ASM, seeking to achieve greater grid stability on the low voltage side of the grid. Indeed, on one hand side, ASM is facing problems due to the growing increase of local energy production from PV panels. And on the other side, the low voltage grid is congested by the high demand posed by the charging of electric vehicles. Thanks to the tools developed by the BD4NET, we are able to manage these two different aspects. Indeed, the first tool is a day-ahead forecasting tool that will take as input the datasets coming from the PV production, the weather forecast data, and the electric consumption of a particular energy district in Terni. The output of this tool will be, of course, energy flow in this energy district. This will be taken as input from a secondary tool, which is the EV charging scheduling model. And this will provide optimized scheduling of the EV charging in order to balance for the local production and achieve greater stability for the grid. The second use case is totally different and see the usage of datasets coming from power data, environmental data such as temperature and humidity, as well as data from noise sensors placed in 10 different substations of the ASM assets. This data will thanks to the training of the model, will allow to assess the aging process and the aging status of those transformers. Also, in this case, will be useful in order to shift the maintenance to a condition-based one. And indeed, predictive maintenance is also the main motivation for the LSP4. OEDAS participates in the similar way, so they will provide data from their SCADA and for from different sources for those assets of the medium voltage grid that are not connected to SCADA. And thanks to the big data analysis and the training of models on those data, OEDAS will be able to act in a predictive way. In particular, the tool developed from the project will allow them to predict when faults on the medium voltage lines will occur. So that's all from my side. Thank you very much for the attention. I will
Thank you very much, Paride. It was an excellent presentation, and I think now we can move on with the next session in the creating of grid data with condition-based monitoring for enhanced predictive asset maintenance, and Niccolò Italiano from RTN. Niccolò?
Yeah. Can you see my screen in presentation mode?
Yes, I think we can.
Okay, perfect. So thank you, Apostolos, for the introduction, and good morning, everyone. I'm Niccolò Italiano, an energy systems research engineer from R&D Nester. And today I will present the details of the developments and results of the Portuguese large-scale pilot, which is named Integrating Off-Grid Data with Condition-Based Monitoring for Enhanced Predictive Asset Maintenance. I will spend first a few words about R&D Nester, my organization, followed by an introduction of the large-scale pilot one, which then breaks down into different use cases. One concerning condition-based monitoring of circuit breakers, and another one concerning semi-automatic maintenance plan for overhead lines. Finally, I will conclude with the results and the next steps foreseen. So, R&D Nester is an R&D center that was incorporated in 2013 in Lisbon and was born from the collaboration of two different entities, being the REN group, Redes Energéticas Nacionais, which is a Portuguese group to which belongs the Portuguese TSO, Transmission System Operator, and State Grid Corporation of China, which is the TSO in China and also the main DSO. In the first year, Nester was initially created to undertake research, development, innovation activities, mostly related with power systems and with transmission networks. But in the last year, we enlarged our vision and we embraced also multiple topics within the energy systems, among which big data and artificial intelligence for energy, which fits with the BD4NET project. So within the project, our main contribution was related to LSP1, which, as Paride mentioned, is part of the BD4NET large-scale pilots, so the pilots for the electricity network. The pilot is located in Portugal and aims to develop condition-based monitoring tools favoring predictive maintenance for two critical assets of the power systems: circuit breaker and overhead lines. Both these two assets are very important for the system and need to be fully operational almost at any time. So any malfunctioning or downtime or extended downtime can cause considerable problem to the system. The pilot partners on top of us were REN, the Portuguese TSO, and Uninova University. So the main challenge we wanted to address here basically concerned the maintenance strategy of system operators for their assets. Nowadays, the strategy are mostly based on a time-based approach in which in-situ inspections or assets replacements are carried out according to a predefined schedule, which regardless of the condition of the real condition of the asset. The main idea here was to leverage the huge data streams that started to be part of energy systems in order to develop to shift to a condition-based approach in order to be able to continuously monitor our assets, so that we could undertake maintenance operation according to really only whenever the asset is needed. And in this way, it's possible to optimize the budget, because not only we are able to extend the operating life of an asset, so not replacing when perhaps it wasn't necessary, the asset was still operating in good condition, and we are also able to replace the asset before a failure actually occurred. And we can reduce the overall downtime, which is usually due also to the conservative nature of the time-based approach. So as I mentioned, our pilot was separated into two different use cases, one concerning circuit breaker and one concerning overhead lines. Use case one aims to use event-based data coming from protection systems in order to create a condition-based monitoring tool and strategy, which is able to evaluate and forecast the operational condition of circuit breakers. On the other hand, use case two was focused on right-of-ways of overhead lines. Right-of-ways is basically the corridors that include the transmission line transporting electricity and the tower, the transmission tower. In this case, we aimed at using LiDAR data retrieved from in situ inspections in order to develop a maintenance plan. Starting from use case one, on the right hand of the slide, you will find a high-level overview of the service we developed. That is basically divided in 4 different submodules. So first of all, we input pre-processed event-based data that comes in the ComTrade format, as we will see in the next slide. We input this to the fault detection algorithm, which serves to basically, first of all, we want to filter out all those events recorded by the protection systems that are actually not faults. Then, in case an event is a fault, we want to understand with a fault classification algorithm whether this event, which type of fault does the event represent it. Then, subsequently, we want to provide an incident report, first assessing whether the circuit breaker activated or not, because it could happen that the fault was just a minor disturbance that does not trigger the circuit breaker. Then we want to extract key incident statistics of the report, useful to evaluate the performance of the circuit breaker and the severity of the fault, such as the opening time of the circuit breaker or the short circuit current. And then finally, using these statistics, we wanted to estimate the state of health of the circuit breaker through the health index estimation, and predict also the future state of health in order to provide predictive maintenance recommendation accordingly. The data set that we used for this were, as I mentioned, ComTrade files, which comes in this very peculiar format, and are generated from the protection systems. So we used 10 years of historical event data provided by the Portuguese TSO, and on top of this, we simulated more than 600 faults in our laboratory using the same format and using a digital twin of the Portuguese transmission network. As you can see, the ComTrade includes a configuration file, which has information such as the name of the signal, the number of the signals, and other metadata, and then the actual data file, which has the actual data and the oscillography of the signals. First of all, we pre-process this data in order to make it into a more human-readable form. And the synthetic ComTrade data is also integrated into the BD4NET platform. So, as I mentioned, the first service is the fault detection. So, for protection systems not only detect faults, but detect an event whenever something happens. And something could happen also when, for example, a circuit breaker is open, intentionally open for a maintenance operation or for a dispatch instruction. In this case, we call this event a planned maneuver. But it can also happen that the protection system records an event when nothing happened, so during a normal operation. I've included these 3 different event types, also including the fault in the table on the right. Then what we did and what the service does, basically, first of all, it standardizes the data, subtracting by the mean and scaling to unit variance. Then apply a Hilbert transform to each current time series. As you can see on the bottom figure, the transform basically computes the analytic signals, so the envelope of the signals, in order to flatten the oscillography nature of the signals, so that change points from the steady state are easier to detect. And then we fit the PELT algorithm, product linear algorithm, to detect the different change points characterizing the signal. According to the number of change point detectors, if there were more than one, we label the event as a fault. Only one, it was just an opening, so a planned maneuver, and 0, a normal operation. And we attain an accuracy of around 92%. Then, if an event is a fault, it goes through the fault classification service, in which we want to understand which type of fault the event is. As you can see, we distinguish 7 types of fault in the table: phase to ground, 2 phase to ground, and 3 phase to ground, according to the different phases. What the service does is, first of all, further pre-process the data, extracting the root mean square value of the currents and the voltage right before and right after the fault occurrence. And then we train the XGBoost classifier using both historical and synthetic data. And then we also apply the early stopping technique in cross-validation to prevent overfitting. And we attained an accuracy of around 96%. On the right of the slide, we can see a confusion matrix for the model, for one of the cross-validation models. Afterward, we have the incident reporting service, in which, first of all, we want to detect whether the circuit breaker is activated or not. To do so, we use the Fourier transform in order to detect abrupt changes, abrupt drops in the frequency that are associated with the opening of a breaker. And then we segment the signals using Waverly transform, in which in this case we detect the exact timestamps for each most significant change point. As you can see in the figure on the top right of the slide, we managed to segment the fault into pre-fault period, fault period, circuit breaker disconnection, and a reconnection. And thanks to this, we are able to extract key incident statistics, such as the detection time, the elimination time, the maximum current, and other important statistics. Then finally, using these statistics, we combine these statistics with operational limits that are defined by circuit breaker manufacturers in the data sheet, or directly by the system operator in maintenance manual, according to the rated voltage of the breaker. So we combine this with the statistics extracted in the incident report, and we adopt a normalized health index approach to evaluate the state of health of the circuit breaker. And in this case, we based within the pilot, we based on the opening time, of the ignition time of the circuit breaker, which is one of the most significant parameter of the performance of the breaker, and it's also an indication of how long the asset connected to the grid withstand the fault. The health index approach allows to use parameters that are independent from the magnitude and the unit of the variable used. Then we define the threshold for maintenance recommendation, as you can see in the figure, and we define this threshold according to the operational limits. And then we fit a degradation model to historical data, assuming an exponential degradation. And the model is able to predict the period of time left before reaching a critical threshold, using also uncertainty ranges to account for uncertainty of the prediction. And then provide a predictive maintenance recommendation using a traffic light label system. So regarding the deployment of our services, we successfully integrated the synthetic data in the BD4NET platform. The preprocessed data is available. And then we deployed also 3 use case 1 services into the BD4NET analytics toolbox mentioned by Apostolos. We integrated the fault detection, the fault classification, and the incident report. This service can run jointly or also separately, or as well integrated within another pipeline, in a personalized pipeline, by using local Kubernetes. More information are included in the description of the services in the toolbox. Coming now to use case 2. Use case 2 concerns right of ways in overhead lines. Basically, it used LiDAR point cloud inspection data, and it's divided in 3 different submodels. First of all, the first goal was to classify the type of transmission tower included in the data. Then we have a classification model that wants to classify each point included in the data in order to understand to which objects it pertains, namely if it pertains to the tower, to the line, to the trees, or to the buildings. And finally, based on this classification of the objects, we're able to develop a maintenance plan based on the distance between these objects. As you can see in the figure, when a tree, for example, is too close to a line, that would trigger maintenance action. So the data that used is LiDAR data, light detection and ranging data, real inspection data that was provided by REN about on inspection on overhead line assets. The data came with 3D coordinates, as you can see in the figure, and also with some metadata, including, for example, the location of line segments and other information. Also, in this case, for this use case, we developed synthetic data, a methodology for synthetic data generation. This was done by Uninova University to overcome the fact that the data used, the LiDAR data provided by REN was under a non-disclosure agreement. And basically, they developed a methodology in which they were used as input. They used as input electrical structures such as towers and lines, and vegetation such as trees and shrubs. And using NVIDIA Omniverse, they carried out a domain randomization in which they simulated multiple scenarios with different sizes of these objects or different type of the objects combined together. And they were able to produce as output fully annotated and multimodal data in the form of RGB image, instance segmentation, or with semantic segmentation, or simple point cloud. The advantage of this is that we are able to produce scalable data sets that also can be tailored to some specific needs and according to how we set up the simulation. So coming back to the development per se, the first service is the classification model for transmission tower types. As you can see in the workflow on the top right of the slide, first of all, we use the point cloud data. We pre-process the point cloud data, applying some technical transformation, such as rotation, calculation of the centroids, reducing dimensionality to a common denominator. Then what we did, first of all, was to manually label the 12 tower types for each LiDAR data, the types, so 12 types of tower that you can see in the bottom of the slide. This was quite a time-consuming process done thanks to Westport from the TSO side. And then based on this, we generated base reference models for each label, as you can see in the slide for the class A2, for the tower A2. Basically, we superimposed different point clouds of the same tower type to generate this model. And then we were able to, when we had a new LiDAR instance, for a new LiDAR instance, we can compute the point cloud distance between this new instance and each base reference model to understand which is the model that is closer to this instance. And so using a modified Universe neighborhood approach. And then vote which is the reference model closest to this instance. And we obtained with this an accuracy of over 89%. The advantage of this model is that it doesn't need a huge amount of data to be trained, because it basically needs mostly only the base reference models. But then, since we had quite extended amount of data available, we also trained machine learning based model, such as random forest, and we obtained an accuracy of over 96%. Subsequently, we wanted to classify unlabeled LiDAR data, as you can see in the workflow in the bottom of the slide. So each point we wanted to know to which objects it pertained. First of all, we extracted some significant features for this, such as eigenvalues, elevation, or the height above ground, verticality of the image. And then we trained 3 different classification modules. We tested random forest, XGBoost, and convolutional neural network. First, we test them on a validation data set. So you can see the first line of the table. And all the models were performing quite well, more than 98%. But then we carried out also sensitivity analysis in order to understand whether the model would perform also or you testing the model on unseen line spans. So we tested the model on line spans that were not 10 line spans that were not included in the training data set. And as you can see in red in the table, the first model underperformed on 3 different lines, while the convolutional neural network kept a robust performance for all the different lines. And so it was chosen for the model. Then, thanks to this labeling, so we were able to detect the models. The model are able to classify each point, as you can see in the figure, and tell me which is the vegetation, which are the lines, which is the tower. And thanks to this, we could develop a maintenance plan by, first of all, computing the relative point cloud distance between lines, vegetation, lines and building, and other objects. Compare this distance with predefined values, so thresholds that are defined by the system operator according to the regulatory framework. And thanks to this, we can detect problems that can pose a safety risk, as for example, a tree that grew excessively close to a line, or a building that was, or an object that was built close to a line. And draw up a maintenance plan accordingly, classifying the events according to the type and also the risk level which we assign to it. To sum up, finally, to measure the result, we used the key performance indicator, KPIs, that were defined at the beginning of the project. As you can see in the table, we managed to exceed all the KPIs for both use cases. And the main result was that we managed to develop 2 automated tools to support system operators for the asset management of their assets. And this enables to optimize the budget allocated for asset maintenance by undertaking maintenance only whenever it's needed. And also our tool, our condition-based monitoring tool, are able to provide prompt reports in a few seconds for the case of circuit breaker. So facilitating and accelerating the manual analysis that is done by operators when an event occurs or when an inspection of the tower is carried out. Finally, the next steps that we foresee are, of course, to try to further improve the performance and accuracy of the services that we've developed. For example, we're already investigating how to which additional factors to include in the and how in the estimation and prediction of state of health of circuit breakers. And then we plan also to use the outcomes of this research, of this pilot, as a benchmark for future more advanced methods related to condition-based monitoring and predictive maintenance, also concerning other aspects of the power system. So that's all, also from my side. Thank you very much for your attention, and I remain available for any doubts or questions concerning the pilot.
Thank you very much, Nicolo, for this detailed presentation. And I think now we can begin with a Q&A session. So perhaps all the participants, they can put questions in the Q&A so that our panelists can answer them. Okay, so I see that we already have questions, and the first one is, can you mention examples of synergies or knowledge-sharing opportunities that have arisen during the project? This is open for answer for everybody who wants to give an answer.
Okay, perhaps I can take it. Okay, so for synergy or knowledge sharing opportunities, we can say that since we are working on the energy sector, we have seen that although not all use cases and challenges are the same, we can see that some data at first and some services, if we modify them somehow, could be able to be shared. In more detail, we have two pilots that work with residential data for flexibility reasons, for different, although different use cases, different approaches. So what we've done through our technological technology tools we have created, we were able to exchange this data, of course, with all the protection. The pilots and the partners that worked on these use cases were able to exchange data in order to test and validate their algorithms in different settings and scenarios. That means that the idea was to take out the bias, to take out the data sample that was in one country and use it with another data sample. Also, this is difficult on a technology level because usually, of course, in the context of different languages, and the data sets how they are, we were able to make them interoperable. But the time series data that usually come from residential consumers or prosumers, we also use that. They have also used that. The time series data provide challenges on how to process them, and in order to insert them into the different algorithms in order to be trained and deployed. This is difficult, but we have managed to do that, and we have tested different algorithms from different pilots from different countries with different training data sets. This is more on a technical scale, but we also have, on a technical scale, this is how we actually use knowledge sharing on different contexts and different use cases, but also on the synergies. Since we have three pillars, we have seen that there is the intention to collaborate more closely for different use cases that each pilot has, because the advancements of the solution we propose to some pilots that have different use case from another pilot, but they can be applied also to different pilots. That means that this analytics toolbox in the marketplace can be, let's say, in a plug-and-play situation. They can understand what has happened in the context of a pilot and take this information, take this already plug-and-play, let's say, service and use it for their own needs.
Thank you very much, Nikos. I believe it was a clear answer and indeed multi-level one, because we can consider also the technical development of BD4Energy and how these layers can be used in other projects, or generally speaking, implementation of this kind of solutions. Another question, do you foresee that these services or similar AI-based services related to power systems will replace human operators in the next future?
So maybe I can answer this. Regarding the service that we developed, I think there can be a really good, really important support for system operators, but I don't foresee the service to completely replace human operators, because our service that these are really sensitive operation when dealing with the maintenance of the system. So it's always important that there is a human check behind this. So a quick answer is no, they will not replace, but it would be a really important support for that.
So it's going to be very helpful, but under no circumstances, at least for the near future, we replace human operators, let's say.
Exactly, yeah.
Okay, excellent. Thank you very much, Nicolo, for the answer. Let's continue with the questions. We have another question. Is it possible to use your tool for protection relay oscillographics analysis also by other TSOs? If yes, how? So how can a TSO acquire the tool?
So the tool currently is available, as I said, in the BD4Energy Analytics Toolbox, can be used following a certain instruction, but after contacting the R&D nester, because since the code is not open source, a password is needed. So for sure, for now can be tested. I will leave a contact on the chat if you're interested, so we can discuss about it. I can send you more information, and then in the next future, after the end of the project, we will elaborate a plan on how to share this with other TSO.
Okay, and just
possible.
additional, let's say, sub question in the same area. What scripting language is the tool written in?
It's entirely written in Python.
Okay, excellent. As expected. We have another question. What did you learn by applying BD4Energy solutions to such a diverse set of pilots in power distribution transmission?
Okay, I can answer that. So, well, first of all, we saw the application of these tools and methods to such a diverse set of pilots. Like all of these pilots not only are operating on different contexts like the TSO and DSO, but they're even participating with different motivation to the project. And what we can learn is that, well, these tools are so useful in such a diverse context. So on one hand, they are very successful. On the other hand, we can really say that there is a need for big data analysis and big data analysis tools, of course, for these applications. Since on the one hand, the digitalization in the recent years brought availability of big data sets, but we still need the tool to exploit in the best way all these wide data sets and, yeah, especially integrate several data sets with diverse origin is something that until recently was not really possible to do with the best results. And now, thanks to these tools, we see that it's this is the way to proceed for the operation of these electric networks.
Okay, so basically, we have seen clear advantages in the implementation and use of these tools in this context, correct?
Yes, I would say so, and clear advantages in such a diverse array of operation activities, and especially in the context of predictive maintenance, but also in several different contexts.
Not only in this pillar, let's say, but all the pillars in BD4Energy, especially in the context of demos.
Yes, this can be extended even further, considering the other pillars of the project. Yes, totally.
And indeed, that was one of the objectives of the analytics part of BD4Energy, but of the project overall. Okay, I believe that we do not have any other questions. So I guess that
not a question. I see that Nicholas shared his email, but it was to host and panelists. Yeah, Zoom has this type of thing. If you can send it to audio, can we send a?
Thank you. I cannot send it. I don't have access to the chat.
Okay. I think now it should be good. And panelists. Okay. Just for everyone to have your email in case they have questions. All right. That was all.
Okay.
okay, perhaps we can recap. We had the opportunity in the context of a BD4NET session to have a, let's say, a first by Nikos approach in the BD4Energy project and what we are talking about when we are talking about BD4Energy. We had the opportunity to see in somewhat more detail the three technical layers of the solution in BD4Energy: governance layer, marketplace, and the analytic toolbox. In the context of analytics especially, we had Parid and Nicolò, which give us a clear, detailed explanation about the work that we have done in this pillar, and especially in LSP1. We had the opportunity to discuss about specific questions that were raised by the audience that give us even more understanding about the implementation, what were the advantages and what were the objectives, what we were hoping to accomplish. And I believe that based on the time frame also, perhaps we could finish with a work session here until I don't see any other questions. So I think that we can finish here, Nikos.
Yes. Thank you all for joining. Thank you for Apostolos, Nicolò, Paride, our host, Chris. Follow us on our social media channels. You can also check our website for our results. And that's it. Thank you all very much for joining this workshop.
Thank you. It was a pleasure.
Thank you very much.
Bye.
Have a nice day.